disturbed during the presentation. Okay, here we go. Hello, everyone. Welcome to the IBPSA-USA Research Committee webinar. For those of us who are joining us live on YouTube, we will get started in just under a minute here. Also live stream.
Okay, we're good to go anytime.
Good to go anytime. Okay, Amy, you can share your screen if you want.
Okay, sure.
Pull up my script here.
Is it showing the PDF?
It is, yes. We're not on, now we're on presentation mode. Perfect, okay.
Let's confirm that the audience can both hear and see. They can put those into chat or raise their hand or indicate in some way.
Yeah, so there is, people are saying yes, they could hear us. That's great. Okay, so let's get started in about right now. Why not? Okay, hello everyone. Happy Thursday. My name is Gokul Paranjoti, and I'd like to thank you for joining this webinar. This webinar is about the optimization for savings in district thermal energy systems by Amy Allen with NREL. This webinar is hosted by the IBPSA-USA Research Committee with the goal to share new ideas from research to the building simulation community. Excuse me there. If AIA continuing education credit is available for attending this webinar, please email info@aiaeb.org with your AIA membership number to receive credit for attending today's event. I will also post the email in the chat so you guys can access it later. So today's speaker is Amy Allen from NREL. She has worked on modeling and software development related to district energy systems in her tenure there. She holds a PhD in architectural engineering from the University of Colorado Boulder. Prior to joining NREL, Amy worked as an engineer at KW Engineering in Oakland, California. If you have questions during this webinar, please type them in the chat window. At the end of the presentation, I will unmute our audience on Zoom for a discussion with Amy. If your questions are through our YouTube live platform, I will ask them on your behalf. With that said, I will mute myself and hand over the baton to Amy. Amy.
Okay, thanks very much, Gokul, and thanks to the research committee for having me. As Gokul said, my name is Amy Allen, and I work as an engineer at the National Renewable Energy Lab. And today I'll be giving a presentation on work that I completed as part of my dissertation at the University of Colorado. And the work was done in conjunction with my advisors and committee members, Professor Gregor Henze and Professor Kyrie Baker of the University of Colorado, and Professor Greg Pavlak of Pennsylvania State University. And in this presentation, I'll be discussing work to develop a topology optimization framework for district thermal energy systems. Specifically, this work sought to develop a framework for addressing the questions in the context of an urban district with known building locations and loads. What is the best subset of buildings to connect to a district thermal energy system? And by what network should they be connected to minimize life cycle cost? And this is what I'll refer to as the network topology optimization problem. In this presentation, I'll talk about the background and motivation for this work, describe my work to validate approaches to each component of the topology optimization problem, and present results from a demonstration of the framework to a case study district, an assessment of the value of topology optimization, and discuss avenues for future work. As many of you are probably familiar, district thermal energy systems have evolved over around 150 years from early systems using steam to supply heating to dispersed buildings. And past studies have generally grouped these systems into either 4 or 5 generations, with the development of these systems through generations characterized by a transition from steam to water as the working fluid, and use of water at increasingly moderate temperatures in both heating and cooling modes. And I'm sorry, I'm trying to get this taskbar out of the way, but what the figure caption says is an attribution of this figure to a paper by Lund and others in 2014. And this figure conceptually shows the evolution of district thermal energy systems over time, with the y-axis showing a qualitative metric for energy efficiency and time along the x-axis. And as these systems have evolved to use water at increasingly moderate temperatures, their energy efficiency has increased through a reduction in distribution losses and compatibility with lower exergy sources of heat and heat rejection. And I'll elaborate more on that subsequently. But to mention now, the primary focus of my work has been on so-called 5th generation district heating and cooling systems, which use water at a range of temperatures of 15 to 25 degrees Celsius or 60 to 80 degrees Fahrenheit. And these systems are also known as ambient loops because they use water at temperatures close to air temperature. And again, I'll try to get the taskbar out of the way of this figure. This figure shows a schematic view of the type of 5th generation district heating and cooling system on which I focused in this work. And this depicts a 5th generation district heating and cooling system configured with a 2-pipe network consisting of a warm pipe operating at around 26 degrees Celsius and a cold pipe at around 16 degrees Celsius, using water as the working fluid, and with the main loop conditioned by a centralized ground source heat pump to temper the water and keep it within this temperature range. 5th generation district heating and cooling systems are characterized by the use of distributed water source heat pumps at connected loads, which further temper the water to meet the building's heating and cooling loads. And as shown in this diagram, this system configuration facilitates both bidirectional thermal flow, meaning that each connected load can exchange heat or provide heat rejection from the network, and bidirectional mass flow, in that the dominant direction of mass flow through the loop would be either from the warm pipe to the cool pipe or vice versa, depending on whether heating or cooling loads are dominant in the system. And 5G DHC systems can operate in a variety of configurations. I focused on systems with parallel connections of loads to the network, meaning that each load effectively sees the same supply temperature from the network and the same return temperature, in that in this case, the mass flow through the energy transfer station connecting the load to the network is controlled to a fixed delta T. But in principle, such systems can operate with loads connected in series, in a single pipe network configuration, and in a configuration with unidirectional mass flow. What's most important here is beyond the specific system configuration, 5G DHC systems in general offer the most compelling application for network topology optimization. And that's due to their nature of permitting connected loads to act as prosumers, or producers and consumers, and offset heating and cooling loads of other connected buildings in a synergistic manner. In that, if Q dot A here, or the load assigned to building A, is perhaps opposite in nature of Q dot B, meaning that building A is in cooling mode while building B is in heating mode, the combined heat and heat rejection draws from each of those buildings can offset the load on the centralized heat pump and improve the energy efficiency of the system's performance. And this characteristic of the systems both complicates their design and also creates an opportunity for potential savings from network topology optimization. And another key attribute of 5G DHC systems is that they facilitate the integration of waste heat sources at increasingly moderate temperatures due to their moderate operating temperatures, which can make sources such as commercial refrigeration and data centers useful sources of heat for these systems, as well as facilitating integration of renewable thermal sources such as solar thermal. And I'll get the taskbar out of the way. The motivation for focusing on district energy systems in general, since this problem is also generally speaking extensible to any generation of district thermal energy system, is that such systems in appropriate applications have been demonstrated to facilitate more cost-effective reductions in greenhouse gas emissions. A study by Connolly and others in 2014 found that the European Union could meet its goals for greenhouse gas emissions reduction at a 15% lower cost through the expansion of existing district heating systems than through building efficiency measures alone. And the scale of district thermal energy systems also creates the potential for more cost-effective utilization of waste heat and renewable thermal sources due to the synergistic ability of buildings to offset each other's loads, and also the presence of a concentrated load in a given location. And many past studies in this area have addressed older generations of district heating systems specifically. But the nature of 5G DHC systems can make their implementation cost-effective at lower load densities than conventional district heating systems would be. And a study by Bufa and others in 2019 found that operating examples of 5G DHC systems in Europe had lower levels of a low density metric, the linear heating power demand density, than typical district heating systems, and then the screening values at which district heating systems would generally be deemed to be cost effective. And that results from the fact that 5G DHC systems can use, in some cases, uninsulated plastic pipe due to their more moderate operating temperatures. And also, since they generally provide heating and cooling from a two-pipe network and permit buildings to offset each other's loads, can provide both heating and cooling more cost effectively than conventional district energy systems with separate heating and cooling networks. Certainly, spatial load density influences the cost effectiveness and practicality of district thermal energy systems. And in the case studies I've considered, I've drawn on past work to identify appropriate metrics for that. But in general, district energy systems show promise for efficiently providing heating and cooling to urban districts. And that motivates my focus on these systems in the context of this problem. The diagram on this slide shows examples of network topologies that commonly occur in the context of district thermal energy systems. On the far left is a radial network configuration, which is typical of older generations of district thermal energy systems, in which a single supply path is needed from each connected load to a central plant. And in older generations of district thermal energy systems, such a grid or network would typically exist separately for the heating and cooling systems. The ring configuration, as the name suggests, provides a central ring off of which connection lines run to individual buildings. And this connection format can be advantageous in terms of providing redundancy through multiple supply paths. And at the far right is a meshed grid in which there exists several potential connection paths from a central plant to each load. And this connection configuration would not typically be considered for earlier generations of district thermal energy systems, but is increasingly relevant in the light of 5G DHC systems due to the ability of connected loads to offset each other's heating and cooling requirements. The consideration of this type of network configuration is motivated because each connected load can also be viewed as a source of heating or heat rejection to other loads in the network. And thus, with this wider search space of network configurations relevant in the context of 5G DHC systems, network topology optimization becomes increasingly important. For the purposes of this analysis, I've chosen to represent network configurations as mathematical graphs or sets of vertices and edges connecting them. And this figure shows 4 example graphs with the vertices as green circles and the edges as purple line segments. And particularly relevant in representing thermal networks is the concept of connected graphs, or a graph in which at least one path exists between any 2 nodes in the network. And one can see that that's relevant in light of district thermal energy systems because there's a necessary constraint that each load served by the network have a path connecting it to a central plant. And subsets of connected graphs include those known as spanning trees, or graphs in which there exists exactly one path and no more than that, connecting each pair of nodes in the network. And in this figure, all 4 of these graphs are connected graphs, and only the top 2 are spanning trees. And within spanning trees is the concept of a minimal spanning tree, or the spanning tree with the least total edge length. And one can see in the context of district thermal energy systems, the minimal spanning tree would provide a required level of network connectivity for buildings in the district, while minimizing the total length of thermal connections or pipes, thus minimizing that component of the infrastructure cost. So the minimal spanning tree graph becomes an important consideration in this context. In graph theory, graphs are often represented with what's called an adjacency matrix, or a square matrix with binary values and dimension equal to the number of nodes in the graph. In the context of district energy networks, the relevant number of nodes would be the number of connected buildings plus 1 for the central plant. And each element of the matrix has a value of 1 if there exists a connection between the corresponding nodes, and a value of 0 otherwise. And this adjacency matrix at right corresponds to the connectivity of the thermal network shown at left. This plot shows the enormous growth in the size of the search space, or the number of potential network configurations for the topology optimization problem, as a function of the number of connected buildings. And this size of the search space grows factorially as a function of the number of connected buildings. And you can see the y-axis here is on a log scale and grows to being on the order of 10 to the power of 190 for 100 considered buildings. And the search space as a whole, or all potential solutions, is shown with a solid line. And restricting the search space to only minimal spanning tree graphs is shown with a dashed line. And that effectively shows the effect of reducing the problem to the selection of the optimal subset of buildings to be connected. And it's worth noting again that I considered both that problem, the selection of buildings to be connected, as well as the network by which to connect them. And one can see that even with the restriction of the search space to minimal spanning tree solutions only, the size of the search space quickly becomes intractable for considering even 10 buildings. So this aspect of the problem motivates the use of network topology optimization, because with this consideration of the full suite of possible network configurations, the problem of selecting buildings to be served by the network and a network to connect them would quickly grow intractable otherwise. And this equation shows how one could evaluate the size of the search space. The term on the right involves selecting the number of graphs to connect a given number of nodes. And it's expressed as I plus 1, with I being the number of buildings to account for the presence of the central plant. And the binomial coefficient here accounts for selecting a subset of buildings to be served by the network. And then at left, one more configuration is added to account for what I've called the null case, in which all buildings are served by independent systems, as that is also a potential design outcome. And unfortunately, there's not a way to evaluate the G of I plus 1 term in closed form, but resources such as the online Encyclopedia of Integer Sequences tabulate this for graphs of up to 18 nodes. And I've used that to calculate the size of the search space for the problems I've considered. And for emphasis, this figure illustrates all possible design configurations considered in the scope of this type of problem for a district consisting of just 3 prototypical buildings and a central plant. And here the buildings are shown with blue nodes and the central plant with a red node. And this amounts to 54 potential network configurations for just this small subset of buildings. And the search space grows factorially as one considers a larger number of buildings. And as one can see here, this search space includes the null case in which no buildings are served by a district energy system, and all other potential scenarios in which some buildings have independent systems and others are served by the network, and then all potential network configurations to connect a given subset of buildings. And this just further underscores the need for an optimization approach to address this problem. Numerous past authors have addressed optimization problems related to district energy systems, including the selection of optimal operating temperatures and integration of different types of primary equipment and waste heat sources. In the area of network topology optimization specifically, most past studies have focused on older generations of district thermal energy systems, and accordingly, often considered only a limited subset of potential network configurations, for example, excluding mesh networks. Past work has often leveraged genetic algorithms for the optimization problem, and past studies have found the optimal configuration to be highly context dependent. Other past studies have called for examination of both aspects of the network topology optimization problem. That is to say, the selection of the best subset of buildings and the best network by which to connect them. And my work here has sought to address that. Here is specifically the objective function that I considered in the context of this problem. And I'll note that this overall framework is generally extensible to other objective functions using energy consumption, energy cost, or carbon emissions as inputs. In this case, I considered a life cycle cost metric, including the infrastructure cost associated with the thermal network itself, energy cost for HVAC, for buildings served by independent systems or served by the district energy system, and a cost associated with a price on carbon, which doesn't currently exist in the United States, but was included to attempt to monetize the benefit of these systems in facilitating reductions in carbon emissions, which they do through, in addition to their energy efficiency, their compatibility with electrified primary equipment, such as heat pumps, which facilitates use of renewable source energy as penetration of renewable electric generation increases. And so the terms of this cost function correspond to infrastructure cost related to the thermal network itself, the ongoing cost of electricity and natural gas for both the connected buildings and those served by independent systems, and the cost associated with the price on carbon. I evaluated the life cycle cost over a 30-year time period, accounting for a 3% discount rate. And these uniform present value, or UPV terms, in the case of the energy cost, account for both the discount rate and projected escalation in the cost of these commodities in the US. And the cost of carbon is a function of time because it accounts for both a carbon tax that varies over time and the expected decline in carbon intensity of electricity in the US. And I'll note that for the purposes of this analysis, I treated any difference in HVAC equipment costs for buildings served by the DES versus buildings served by independent systems as being negligible over a 30-year time frame. And this is certainly an assumption that could be refined in future work. The constraints here address the structure of the adjacency matrix itself. I've made a simplification to use only the upper triangular elements of the adjacency matrix as optimization variables, since by definition, it's a symmetric matrix. Because thermal connections are defined here in terms of just their existence, though in practice, they may facilitate bidirectional mass flow. Of interest here is simply whether they exist or not. So there's not a relevant element of directionality. By definition, if a building is served by the district thermal energy system, there must exist a path through the network connecting it to the central plant, which is expressed in constraint 3. And constraint 2 simply addresses the construction of the adjacency matrix. And this table, I'll get the taskbar out of the way, shows the value of relevant high-level parameters in the cost function, including the discount rate and utility cost in the base year. The utility cost and the carbon pricing scenario were obtained from scenarios used by the federal government in a life cycle costing handbook that they produce, which is the Lavafa and Neefel reference. And values obtained from the Energy Information Administration were used to set the base cost for a location in Colorado. I first sought to validate the approaches to the optimization problem. That is the use of the minimal spanning tree heuristic to select the optimal network, and particle swarm optimization to select the best subset of buildings to be served by the network, with an exhaustive search that is considering all potential network configurations for a 5-building prototypical district. And I populated this district with building models available through the US Department of Energy's prototype building models, and then use these models and a parameter suite to create a data set that was used to train random forest meta models using the meta modeling framework created by my colleague Nick Long at NREL. And these data-driven meta models then provided a computationally efficient way of predicting building thermal loads as a function of network temperatures in the ambient loop. And these could be readily integrated with a model of the district thermal energy system created in Medelica, which I extended from a model originally created by Eustace van Rijn, another student who worked in Professor Hens's group. And for purposes of calculating pipe lengths, I've plotted the locations of these buildings on a real block in Golden, Colorado, but they're not intended to represent the characteristics of actual buildings at this location. And based on evaluation of a load diversity metric, since, as one might expect, higher levels of thermal load diversity create greater potential savings from 5G DHC systems, I populated the district with a hospital building, 3 multifamily buildings, and a retail building. And the central plant is also shown with a gray rectangle. I used an energy model in Medelica to represent the performance of the 5G DHC system, and then use the energy consumption results as inputs to the cost function. And the system configuration that I considered is similar to that shown on this diagram earlier, with the warm pipe and cold pipe of the system operating at the temperatures shown, with bidirectional mass flow permitted through the network, and the energy transfer station with heat exchangers and circulation pumps and water source heat pumps at each building, controlling mass flow to maintain a 10 degrees C delta T across the building. This table summarizes characteristics of the prototypical buildings considered in this study. And for purposes of representing buildings with independent HVAC systems, their baseline HVAC systems in the prototype building models were preserved. And for purposes of representing the buildings served by a district thermal energy system, the building models were modified to leverage hydronic systems with water source heat pumps tied to the ambient loop. And I'll try to get the taskbar out of the way. This plot shows a disaggregation by heating and cooling of the source HVAC energy use intensity for each of the prototypical buildings in their connected and independent states at both the site and source level. And it's worth noting that use of the district thermal energy system resulted in at least a slight reduction in EUI across all of these buildings and metrics. But the most significant reduction was observed for the prototypical hospital building, primarily due to its high levels of internal load diversity, in which the water source heat pumps serving its zones operated in a way that was somewhat analogous to the 5G DHC loop as a whole, and allowing loads from zones in opposite modes to offset each other. And this has been observed in past work as well. And this plot summarizes results from this exhaustive search, which considered over 30,000 potential network configurations for the prototypical district, and plots each solution in terms of the associated network length and the associated life cycle cost, with the null case shown with a black cross. And as one can see, a bifurcation exists here as to whether or not the prototypical hospital building is served by the network, with the scenarios in which the hospital building being served by the network have a significantly lower life cycle cost. And that results from the fact that only that building type exhibited a reduction in energy cost from a connection to the network, driven by its significant reductions in energy use intensity, which offset the increase in energy costs due to the higher unit cost for heating with electricity relative to natural gas in this location in the US, and true in many areas of the US. And one can also observe here a trend of increasing life cycle cost as a function of network length due to the increasing cost associated with the thermal network, scaling with the length of the network based on how I've defined it. And this plot shows the district level HVAC source energy use intensity for all solutions as a function of the network length. And one can see here again the same trend of bifurcation between scenarios in which the hospital building is served by the network versus by independent systems. And this bears out the trend of the hospital building having a lower source EUI when served by the district network. And its significantly higher EUI and loads drive that result for the network as a whole. And it's worth noting that the null case exhibits the highest source energy use intensity for HVAC. This plot summarizes the results for the evaluation of the minimal spanning tree heuristic. In that, for each potential network scenario, I assessed whether or not the minimal spanning tree network indeed resulted in being the least life cycle cost network to connect the given subset of buildings. And I found that to be the case for all potential subsets of the district. And this is represented in this plot with a metric I call the minimal spanning tree ratio, or the ratio of the life cycle cost of a given network scenario to that of the corresponding minimal spanning tree. And the fact that this metric never takes on a value lower than 1 affirms the validity of the heuristic. I'm sorry, I'll get the taskbar out of the way. With the minimal spanning tree heuristic validated, I turned my attention to the aspect of the problem of selecting the optimal subset of buildings to be connected to the district energy system. And I sought to address this with particle swarm optimization, or PSO, which is a meta-heuristic approach in which elements of a swarm of animals that could exist in the natural world can be conceptualized as evaluating candidate solutions in the search space, which they move through at some velocity. And each particle maintains a memory of both its best prior location with respect to the objective function value and the best prior location evaluated by any element of the swarm. And so in the context of binary valued variables, since I'm considering the elements of the adjacency matrix as the optimization variable, the optimization algorithm takes on this formulation with a probability of a given element flipping from 0 to 1 or vice versa, and the velocity of particles through the search space evaluated as shown here. And it's worth noting that, like other meta-heuristics, PSO includes a stochastic element, which mitigates its risk of getting stuck in a certain area of the search space and helps to balance what are called exploration and exploitation, but also results in the fact that there's no mathematical guarantee of convergence at a global optimum. But with an exhaustive search analogous to the one to validate the minimal spanning tree heuristic, I sought to evaluate the performance of PSO in the context of this problem. I selected values of the PSO hyperparameters based on a review of literature and selected the values shown here in this table. And these tables or these plots highlight the results of the validation of PSO, which I performed for 5 different scenarios, which were distinguished by different values of the high-level parameters, such as utility cost in the life cycle cost function, and were selected so that each one resulted in a different optimal value of buildings connected to the network. And I've numbered them here accordingly, with scenario 0 being a set of parameter values that resulted in an optimal connection of no buildings to the network, etc. And as shown here, within 100 iterations of the algorithm, for each of these scenarios, as well as the others, the algorithm converged to either the global best value shown through the exhaustive search, or a value within a marginal difference from that value. So the algorithm was deemed to perform well and to converge within a fairly limited number of iterations. As one can see, even after reaching the global best value or one close to it, the algorithm continues to hunt through the search space as shown with these blue asterisks, due to its stochastic nature. But in all cases, was deemed to perform well in addressing this problem. I also extended the analysis by considering an additional constraint to perturb the problem, and the algorithm continued to perform well. I can revisit this later on if there's interest, but I think I'll move on now for the sake of time. Another important result from this analysis was quantifying the value of topology optimization. And for these same scenarios as described earlier, I've plotted here the variation in life cycle cost and also in lifetime carbon emissions for each of these scenarios. And as one can see, the variation is quite significant, motivating the use of topology optimization to choose scenarios with lower life cycle cost or also with lower carbon emissions. And the objective function could easily be adapted to focus solely on that or to weight carbon emissions as a greater component of the objective function. This diagram shows the workflow of the network topology optimization framework, and that it takes in as inputs from the user an energy model in functional mock-up unit format to evaluate the energy consumption element of the cost function, some high-level configuration parameters, and the framework then proceeds to use the PyFMI Python package to modify the FMU to reflect a given candidate solution, which is now restricted to minimal spanning trees based on validation of that heuristic, and uses particle swarm optimization to select a candidate solution in terms of buildings to be connected to the network, and then repeats this process through iterations, which can be terminated either based on a maximum number of iterations or several other criteria, which I can elaborate on if there's interest. And then after the algorithm terminates, returns the adjacency matrix and objective function value corresponding to the optimal solution. And this equation shows the cost function as implemented after the validation of the minimal spanning tree heuristic. And the most important difference here from the earlier formulation is that the dimensionality of the problem is reduced. So the optimization variable now consists of a vector in which each element corresponds to the connectivity of a given building. So the dimensionality of the problem has now been reduced to n+1, considering n buildings and the central plant. And these other slightly different constraint formulations mainly shake out from that. And I can elaborate more on that if there's interest, but for the sake of time, I'll go on to a few more results. I sought to demonstrate the performance of the topology optimization framework as a whole in the context of a larger 7-building prototypical district, with these building types selected to correspond roughly to existing buildings at a location on the CU Boulder campus. And with the validation that these buildings' load profiles were such that conventional screening for district thermal energy system viability would deem them to be a valid application. And so I sought to compare the performance of solutions identified by the topology optimization framework to several base cases or different network configurations serving a district in which all 7 of these buildings were connected to the central plant. And for this purpose, I considered prototypical office, multifamily buildings, and a restaurant. And this table summarizes the attributes of those prototypical buildings, once again leveraging the DOE prototype buildings and the meta modeling framework developed by Nick Long. These plots compare the energy use intensity of each prototypical building in its connected and independent states. And once again, each of these building types shows a benefit in reduction of source EUI for HVAC through a connection to the district thermal energy system. And this plot shows high-level results from this analysis, with blue asterisk showing the best solutions returned by the topology optimization framework. And I say solutions because there were 4 solutions with very similar values of life cycle cost, as well as the base case scenarios, which are shown with squares. And one can see that the full mesh network scenario in the base case entails a very long network and a very high life cycle cost. And thus, this case would probably not be considered as a practical scenario, but it represents one of the extremes, so to speak, of network connectivity, with the base case at the other extreme being a minimal spanning tree network connecting all of the considered buildings, which is shown with a green square, which has a lower life cycle cost, but a still higher cost than that of the optimal solutions identified by the framework. And this plot zooms in on those 4 solutions identified by the framework with very similar values of life cycle cost. And one can see that the solution with, in fact, the lowest overall cost is the null case, in which no buildings are served by the network. And the closely competitive scenarios entail a very limited network connecting either only 1 or 2 buildings. This box plot shows the range of district source HVAC EUI as a function of the number of buildings connected to the network, which emphasizes this trend of a greater number of connected buildings resulting, as expected, based on the individual level buildings results, in a lower overall source EUI for HVAC. And this also affirms a trend observed in the previous case study, which was that in these cases, the selection of a subset of buildings to be connected to the network is much more influential on energy use and life cycle cost than the network by which they were connected. This plot shows a disaggregation of life cycle cost by component for a subset of the solutions considered by the optimization algorithm. And one can see that energy costs are a dominant component of life cycle cost, followed by cost associated with infrastructure and those with a price on carbon. I also considered a sensitivity analysis for the price on carbon and the unit infrastructure cost of the thermal network. And in both cases found that either a very high price on carbon would be necessary for the connection of a large number of buildings to be cost competitive, or correspondingly, a very low unit cost for piping and trenching in order for a large network relative to the number of buildings in the district to be cost optimal. And I'd also like to highlight a few novelties of this contribution, which include the representation of building loads in a nuanced manner and in a way that's flexible to a variety of underlying system energy models. The application to near ambient temperature systems, which present the most interesting application for this work, and the accounting for interactions between building loads and the district energy system, which highlight some of the key elements of 5G DHC systems in terms of the ability of connected buildings to offset each other's loads. In this assessment of the value of topology optimization, I found that the selection of loads to be served by the network is often more influential than the network by which they are connected. As shown in the box plots, the search space of potential network configurations can have wide variation in lifecycle cost and source EUI for HVAC, motivating the need for network topology optimization. And the low unit cost of natural gas relative to electricity creates a barrier to cost-effective heating electrification in this location considered in Colorado and many parts of the US. I can come back to this if there's time, but the ultimate goal is to integrate this work with NREL's UrbanOpt advanced analytics platform. And in conclusion, I'll note that this work has highlighted the potential for network topology optimization to reduce lifecycle cost and energy use intensity through integrating 5G DHC networks as an alternative to independent building level systems. And in the 7th building case study that I discussed, the topology optimization framework identified solutions with lifecycle costs of 14 to 72% lower than that associated with the base cases, depending on the choice of base case. And ongoing work has considered the integration of waste heat sources, which can further improve the energy efficiency and cost effectiveness of 5G DHC systems. And a post-processing framework has been developed to extend the robustness of the exhaustive search by considering a wider range of hyperparameter values in the lifecycle cost function, and to further affirm the validation of the minimal spanning tree heuristic and particle swarm optimization. Okay, thanks very much. That's my presentation, and I apologize for going over time.
No problem, Amy. Thank you. Oh, there is feedback from my end. Okay, no problem, Amy. Thank you so much for your presentation. That was really interesting. We have a couple of questions here. I wanted to ask if you had some time after the top of the hour to answer
of course.
these. Okay. So while our attendees are preparing their questions, and before I ask some of these questions on their behalf and ask them to unmute themselves, I had a couple of announcements too. For those of us who will be leaving us at the top of the hour, thanks to you for joining this IBPSA-USA Research Committee webinar. If you enjoyed this webinar, please consider joining the IBPSA-USA Research Committee. Email research@ibpsa.us or visit the link in the Zoom chat for more information. For those of you watching us on YouTube Live, please like the video and subscribe to our YouTube channel. Our next month's presentation will be from Abigail Safa. She presents on building energy modeling and closure-related applications in historic building renovations. Looking forward to that as well. So back to this presentation. Amy, I had a couple of questions. Hang on while I give the participants permission to unmute themselves. Okay, right. The first one was from David Potterson. And David, let me know if you can unmute yourself, and if so, go ahead and ask your questions. I think you had a couple there. Oops. David says he can't. How about now, David?
Yeah, I think that worked. Can you hear me?
Yep.
Yeah.
Okay. So my big question was, does all of this optimization work take into account? Is it all only for a fixed set of buildings, or does it take into account how to grow the network over time? At Excel Energy, we're looking at this model. We're interested in this model, but our plan would be to sort of grow it and interconnect over time. It wouldn't just be a fixed yeah, it wouldn't just be a fixed location. It would sort of expand as time goes on.
Thanks, David. That's a good question. And no, it doesn't. This framework is structured, yeah, as you said, to take as inputs, fixed building locations and loads. In practice, of course, one could, set those up to be, to include buildings that might be developed in the future, but that the idea of extending an existing network is a very interesting one. And I haven't considered that so far, but that is a good area for future work.
Got it. Thanks a lot.
Yeah, of course. Thank you.
David, was that all your questions, or did you have others? Okay. Our second question was from Scott Hartsfield. I'm gonna allow you to unmute yourself, Scott. In just a second, you should be able to ask your question now.
Can you hear me now?
I can.
Hey, Scott.
Yes.
Yeah, I can hear you.
I just heard the "can you hear me now?" I did not hear a question. So. Okay, I believe Scott might, if Scott's having trouble, I can ask his question, Amy. He asks, what are the primary obstacles to decarbonization of these types of systems?
Thanks for raising that. That's very important point. And in terms of obstacles to cost-effective decarbonization, which is one facet of it, the high cost of electricity relative to natural gas in much of the US is a key obstacle. And, as I mentioned, the price on carbon that I considered was, of course, fictitious. And so without wading too much into policy, the absence of a price on carbon doesn't allow the benefits of decarbonization to be directly monetized. So that represents an obstacle, and the high unit cost of electricity relative to natural gas, further contribute to that obstacle. And the infrastructure cost associated with networks such as these can also present an obstacle to cost-effective decarbonization. But the analysis of the exact trade-offs between those costs and potential cost savings at the building level through centralized HVAC equipment are very location dependent, but are also, a worthwhile area for future refinement. And refining the cost function in that way could, of course, affect the results of the optimization analysis.
Thanks, Amy. Scott, I hope that answered your question. Our next question is from Yannick Wack. Yannick, you should be able to unmute yourself. Go ahead and ask your question.
Yeah. Am I unmuted?
Yep, I can hear you.
Thank you for the nice presentation. I have a question regarding the scaling you showed. I think you showed it also in your plot. These heuristics you're using, they scale quite steeply with the size of the problem. How do you expect, because I saw you used the 7 consumer case, how do you expect this to perform on larger district heating networks that have like a few hundred consumers, for example? Would that still be usable there?
Yes, thanks for asking that. That's a very important consideration. And sorry, I'll see if I can go back to the plot easily. The minimal spanning tree heuristic does successfully reduce the size of the search space significantly, but as you noted, it still becomes intractable quickly. But in general, the particle swarm optimization algorithm seems to work fairly efficiently computationally. So that, in conjunction with the minimal spanning tree heuristic, made the problem fairly tractable at the scale that I considered, which, as you pointed out, were fairly small. But I expect that with the optimization algorithm, the scale of 20 to 30 buildings would also be readily considerable from a computational perspective, but I haven't dug into how that might scale with a larger number of buildings.
Yeah, thank you. It's just, I think this might be just a theoretical boundary you have with heuristics in general to be considered. But thanks.
Yes, thank you.
I was on mute, so I couldn't ask that question. So I believe those are most of our questions, Amy. I have some, but I could, in the interest of time, I could always catch up with you later on this. If there are no questions, and I'm gonna just do a final sweep of our YouTube live to see if there are questions coming from there. Nope. Okay. Okay. So in that case, thank you so much once again, Amy, for the presentation. Really enjoyed it, and great questions to those who asked. Thanks for being a part of this conversation. See you next month on April 28th, when Abigail Safa presents on envelope considerations for historical building renovations. Thanks, Amy.
Okay, thank you, Gokul. Thanks, everyone.